All right, in this video, we're going to talk about a really cool phenomenon called refraction. So refraction, spelled this way, refraction is a little bit different than reflection. The definition is here. It's the bending of a wavefront as it passes between two substances in which the speed of the wave differs. And we'll get into the details, but I want you to see this in action. So watch this video and you can see refraction in action. So what you're looking at is you're going to see a helium neon laser being shined into a tank of water. The lights are off. And you can see the laser light bends as it enters and leaves the water. You can clearly see it there. The path of the laser bends when it enters the water, and this is refraction. Here's a red laser. You can see it comes up here and then bends. Comes up and bends. Okay, it's also reflecting off of the surface of the water, so we get this second beam, and we'll talk about this, but this is refraction, the bending of light. To understand refraction, we first have to understand how does light travel through different substances. If you remember, light's an electromagnetic wave, so it doesn't need a medium. Well, what does it do when it encounters a medium? You can see this visual will help you understand what happens. When a photon of light hits an atom, here's an atom, the atom begins to vibrate and eventually will emit a photon which the next atom in the substance will absorb and then emit again. And so light passes through substances by a series of almost infinitesimally quick absorptions and emissions of a photon. But this does take time to travel through a substance. And so whenever light approaches a medium, it slows down. Now, different mediums slow light down different amounts, but you can see this process will slow light down. So we can see in this animation the effect of refraction. Here comes, so in this case, we have two mediums. Whoops. And this medium and in this medium, the speed of light is the same. And so light doesn't slow down at all. And so what we see is the light ray, this is a light ray, goes straight. The whole blue thing is the light ray, by the way. And so we can see that since the medium, since light has the same speed in both mediums, there's no refraction. There's no bending of the light. What happens if I change the properties so that this second medium, that light has a that light moves slower? Well, what we'll see is since light moves slower in this medium, that when light travels from this medium to this medium, the light bends. And the reason is, and you can see it here as this animation plays, check out what's happening here. Here comes our wave of light. You'll see it here. This part of the wave gets to the medium first. And because it gets to the medium first where it slows down, it slows down. Meanwhile, here, let's increase the angle so you can see it better. Here we go. So watch. Okay, so what you see what's happening here is this part of the wave of light got to the slow medium, or we say the more dense medium, right? Because light slows down, it's more dense, has more atoms to get through. It slows down, and so the light ray bends towards this medium. And this is a very good illustration to kind of keep in mind as we go forward. Now, why would the light ray bend like that? Well, I have another analogy to help you kind of visualize what's happening when something's refracting. If you've ever mowed a yard in the summer, you've probably experienced this. As you push the lawnmower on cement where it moves quickly, you approach the grass. Well, when you approach the grass, this left wheel, or this bottom wheel, hits the grass first and slows down. Or sorry, this wheel hits the grass first and slows down. And so the path the lawnmower takes is like this, and then it bends this way. Okay? And then when we get to the grass again, now this wheel hits the cement first, speeds up, and the lawnmower bends down again, okay? So when we're talking about bending, we also want to make sure that we draw a normal line between the surface, between the two mediums, so that we can see whether the light is bending towards or away from the medium. So here's a visualization of this same effect.
The two wheels of the mower that are on the pavement are moving faster than the two wheels that are in the grass. Because of this difference in speed,
you see here as the lawnmower travels between the cement and the grass.
Once the wheels reach the opposite line of the pavement, the mower will again
the speed of the wheels change. So now this wheel is moving faster. You can see it better here.
Here's that same
this wheel is moving
from
faster,
a different angle.
So the lawnmower turns this way, bends this way. When this wheel hits the cement, it now begins moving faster, and the lawnmower turns back. This is refraction in action. Like I was saying, it's important when we talk about refraction, we have our incident ray. It's important to draw a normal line between the interface between the two mediums. In this case, medium 1 is air and medium 2 is glass. And so this is our incident ray. This angle is called the angle of incidence. The light ray bends down, and this is called the angle of refraction. And this is called the angle of refraction. So, also interesting, glass is more dense. So we say this is the dense substance. And so light is slower in the denser substance. So when light goes from air to glass, it slows down. And what you notice is that it bends towards the normal. In other words, this angle will be less than this angle. The angle of incidence will be greater than the angle of refraction. And this is true in all cases. So if the opposite situation is occurring, if light is going from glass to air, since the light wave is speeding up in the air, it will bend away from the normal. Now you can always, if you're not sure which way it's going to bend, I draw the two lawnmower wheels on there, and you'll see that this wheel is going to hit the air first, and air is less dense, right? Remember, glass is the dense substance. And so this wheel speeds up before this wheel does, and it bends away from the normal. I have two mnemonics here to help you remember this. Fast, slow, towards. The mnemonic is freaky science teachers. SFA, slow, fast, away. You can think of Sarah farted. Away, away. And that's not any particular Sarah in any class I've ever taught, or even in this year's class. That's just a general Sarah that I've never taught. So don't worry. None of my Sarahs would do that. But Sarah, fart, away. Freaky science teachers. Fast to slow, towards, slow, fast, away. Let's put this to practice. So here we have three diagrams. Medium 1 is the more dense medium. Medium 1 here is less dense. And then light travels faster in medium 1. So take a second, pause the video, and see if light's going to bend towards or away the normal. And draw the ray in. If you want to take a screenshot of this or just do it on paper, but take a second and try it. Okay, you should have had as your answers. In the first situation, since light is speeding up when it gets to medium 2, it speeds up, it goes away, right? So we're going slow, fast, away, SFA. Here we have light coming in, and since medium 1 is less dense, that means medium 2 is more dense, so light slows down, so the ray of light will bend towards the normal. And then situation 3, light travels fastest in medium 1, so it's faster here, slower here, and that again is towards the normal. So that's how refraction conceptually works. So how do we know how fast light travels in different substances? Well, luckily for us, there's a way to calculate it. Here's an equation for your equation sheet. This is a great equation. It gives you a value n, which is known as the index of refraction. And that's basically a ratio between the speed of light in a vacuum, which is its fastest possible speed, right? We know this speed to be 3 times 10 to the 8th meters per second, and that's divided by the speed of the light in that medium. And so that tells us the slower this light travels in the medium, the smaller this number, the bigger the index of refraction. And so we can see some common substances on here, which is pretty interesting, right? We see air has an index of refraction of 1.000293, which means light travels about as fast in air as it does in a vacuum. However, we look at a diamond, and diamond is awesome. It's 2.49. What does that mean? Well, and so we see the speed of light in a diamond, even though it's really, really fast, is not close to the speed of light in a vacuum, okay? So this is why diamonds are so valuable, because essentially light slows down so much in a diamond that it gets trapped for a split second, a tiny, tiny bit of time, and exits the diamond at a different angle. And so we see it as a sparkle, and ooh, and ah. So diamonds are forever, and so is physics. I hope that was fun. I'm going to leave you with a little bit